Welcome to a fascinating journey into the invisible world of biomining, where microscopic bacteria are transforming the mining industry as we know it. Today, we'll explore how these tiny organisms, invisible to the naked eye, are solving some of the biggest challenges in metal extraction, potentially revolutionizing an industry that has remained largely unchanged for centuries. From reducing environmental impact to making previously unprofitable deposits economically viable, these bacterial miners are working at the molecular level to reshape our approach to harvesting the Earth's precious resources. In the shadows of massive mining operations with their enormous machinery and dramatic landscape alterations, a quieter revolution is taking place at the microscopic level. Biomining, the use of microorganisms to extract metals from ore, is gaining significant traction as companies worldwide seek more sustainable and efficient extraction methods. The concept might sound like science fiction, but it's rapidly becoming an industrial reality. These invisible miners are helping us rethink one of humanity's oldest industries, proving that sometimes the smallest solutions can address the biggest challenges. As global demand for metals continues to rise while high-grade ore deposits become increasingly scarce, these microbial miners offer a sustainable alternative that operates at the molecular level, potentially transforming mining economics and environmental impact simultaneously. The stars of this microscopic workforce are chemolithotrophic bacteria, with Acidithiobacillus ferrooxidans leading the way. These remarkable microorganisms possess unique abilities that make them perfect for mining operations. They can oxidize iron and sulfur compounds while thriving in highly acidic environments that would be lethal to most other life forms. What makes these bacteria particularly valuable is their ability to essentially eat the minerals binding valuable metals in ore, releasing gold, copper, and other precious metals in the process. This approach is especially powerful because these microbes can extract metals from low-grade ores that would be economically unfeasible to process using conventional methods. Recent advancements announced by Biomining Solutions, a Chilean-Canadian venture, have improved extraction efficiency by an impressive 37% compared to results from just 2 years ago. This rapid improvement curve suggests we're just beginning to understand the potential of these bacterial miners. The mechanism behind biomining is fascinating in its elegance and simplicity. These specialized bacteria oxidize the sulfide minerals that typically encase valuable metals, converting insoluble metal compounds into soluble forms that can be easily separated from the remaining rock. This isn't a new process, it occurs naturally in some environments, but mining operations have learned to accelerate and optimize these reactions by carefully controlling temperature, pH levels, and nutrient availability. What makes this approach particularly efficient is that these bacterial communities become self-sustaining workforces. They reproduce exponentially under favorable conditions, creating a biological system that continues to grow as long as there are minerals to metabolize. Unlike mechanical or chemical processes that require constant energy input, these bacterial communities actually become more efficient over time as they adapt to the specific mineral composition of each deposit. They essentially evolve to become better miners, tailored specifically to the chemical makeup of whatever ore body they're working on. Traditional mining operations are notorious for their environmental impact. From toxic chemical runoff to massive energy consumption, conventional mining often leaves a significant ecological footprint. A standard gold mining operation can use millions of gallons of water daily and release considerable amounts of mercury and cyanide into the environment. Biomining offers a stark contrast, requiring significantly less energy, producing fewer greenhouse gas emissions, and often operating without the harsh chemicals used in conventional extraction. The process has proven particularly effective for copper and gold extraction. According to recent industry data, approximately 15% of the world's copper is now extracted using bioleaching techniques, a percentage that continues to grow each year. The World Resources Institute estimates that widespread adoption of biomining could reduce mining-related carbon emissions by up to 30% in applicable operations. This represents a significant contribution to the industry's sustainability goals, especially as mining companies face increasing regulatory pressure worldwide to reduce their environmental impact. In an era where environmental considerations are becoming as important as economic ones, biomining offers a path forward that addresses both concerns simultaneously. Beyond reducing carbon emissions, biomining offers other environmental benefits that are increasingly valuable in our resource-constrained world. One of the most promising applications is applying these techniques to mine tailings and waste rock, the massive piles of discarded material from previous mining operations. These tailings often contain residual metals, but at concentrations too low for conventional recovery methods to be economically viable. These sites represent both an environmental liability and an untapped resource. By deploying microbial extraction methods, companies can simultaneously remediate these sites while recovering valuable metals, effectively transforming environmental problems into economic opportunities. Several operations in Australia and Chile have already demonstrated the viability of this approach, recovering millions of dollars in metals while reducing the acid drainage and heavy metal leaching that often plague abandoned mining sites. This dual benefit of remediation and resource recovery makes biomining particularly attractive for addressing the estimated 500,000 abandoned mines in the United States alone, many of which continue to cause environmental problems decades after operations ceased. The economic implications of biomining technology are particularly significant for developing nations with substantial mineral resources but limited capital for large-scale mining infrastructure. Countries like Peru, Ghana, and Mongolia are already implementing pilot programs, with Ghana's Ashanti region seeing a 22% increase in gold recovery rates from previously abandoned tailings. Biomining requires less initial capital investment than traditional mining operations, potentially democratizing access to mineral wealth that has historically been controlled by large multinational corporations. The International Mining Consortium projects that biomining could create over 100,000 new jobs globally by 2030, many in regions currently struggling with poverty despite their mineral riches. The reduced infrastructure requirements make biomining operations particularly suitable for remote areas where building conventional processing facilities would be prohibitively expensive. In mountainous regions of Peru, community-based biomining initiatives have enabled local populations to participate directly in the mineral economy rather than merely providing labor to foreign-owned operations. These smaller-scale operations can be established with investment levels accessible to local entrepreneurs or cooperatives, creating a more distributed pattern of economic benefit. Furthermore, the technical skills required for biomining create opportunities for higher-paying jobs in biotechnology and environmental management, potentially elevating the socioeconomic status of mining communities beyond the traditional roles of manual laborers. Despite its promise, biomining faces significant hurdles before it can achieve widespread adoption. The process is generally slower than conventional methods, with extraction times measured in weeks rather than hours. This extended time frame can be challenging for mining operations accustomed to rapid production cycles. Temperature sensitivity is another issue. These bacterial systems typically perform best within specific temperature ranges, and maintaining optimal conditions can be difficult in varying climates. The need for specific environmental conditions also limits where and how these techniques can be deployed effectively. Researchers are actively working to overcome these limitations. Teams at the University of California, Berkeley, and the Chinese Academy of Sciences are developing genetically modified bacterial strains that can work more efficiently and under a broader range of conditions. Early results from these research programs suggest that these enhanced microbes could reduce processing times by up to 40%, making biomining more competitive with conventional methods. Other research focuses on creating more resilient bacterial communities that can withstand environmental fluctuations without significant drops in performance. These improvements will be crucial for biomining to move from a niche application to a mainstream extraction method capable of processing a wider variety of ores under diverse operating conditions. In perhaps the most futuristic application of this technology, astrobiology researchers are exploring how biomining techniques might eventually be applied to asteroid mining or resource extraction on Mars, where conventional mining would be prohibitively expensive or logistically impossible. NASA's recent experiments on the International Space Station have demonstrated that these bacteria can function in microgravity environments, opening possibilities for extraterrestrial resource extraction that seemed like science fiction just a decade ago. The potential for using biomining in space exploration addresses one of the fundamental challenges of establishing a permanent human presence beyond Earth: the enormous cost of transporting materials from Earth's surface. If astronauts could extract metals and other resources from asteroids or planetary surfaces using bacterial systems, it would dramatically reduce the payload requirements for extended missions. These systems could potentially be self-sustaining, requiring only minimal inputs once established, making them ideal for long-duration space missions where resupply opportunities are limited. While commercial space mining remains years away from implementation, the groundwork being laid through current biomining research may ultimately enable human civilization to access the vast mineral wealth of our solar system in an economically viable and environmentally responsible manner. Microbial mining represents a powerful example of how biological processes can be harnessed to address industrial challenges in ways that benefit both the economy and the environment. As the technology matures and overcomes current limitations, it has the potential to fundamentally reshape how the mining industry approaches metal extraction. The convergence of microbiology, materials science, and mining engineering is creating new paradigms for resource utilization that align with principles of sustainability and circular economy. While biomining won't completely replace conventional mining methods in the near term, its growing role in the industry signals a shift toward more sophisticated, environmentally conscious extraction technologies. Companies that embrace these biological approaches may gain competitive advantages as regulatory pressures increase and consumers demand more responsibly sourced materials. The mining industry, often viewed as inherently destructive and resistant to change, is demonstrating through biomining that innovation can lead to more sustainable practices without sacrificing economic viability. In fact, as ore grades decline worldwide, these biological approaches may become not just environmentally preferable but economically necessary. The tiny miners working at the molecular level may ultimately have an outsized impact on one of humanity's oldest industries, proving once again that in the natural world, the smallest organisms often drive the most significant changes. As we've explored throughout this journey, biomining represents a remarkable convergence of biology and industry, where microscopic organisms are helping solve macroscopic challenges. These bacterial miners are not just a scientific curiosity but a practical solution to some of mining's most persistent problems: environmental damage, resource inefficiency, and economic barriers to entry. From recovering metals from waste to potentially enabling space exploration, the applications continue to expand. While challenges remain in scaling and optimizing these biological systems, the trajectory is clear: we're moving toward a future where extraction technologies work with natural processes rather than against them. The mining industry, one of humanity's oldest economic activities, is being transformed by some of Earth's oldest inhabitants. These invisible miners remind us that sometimes the most powerful solutions come from understanding and harnessing the natural processes that have been perfected over billions of years of evolution. As we face increasing resource constraints and environmental challenges in the 21st century, biomining offers a compelling example of how innovation can align economic and environmental interests, creating pathways to more sustainable resource utilization for generations to come. Thanks for watching. Please like, subscribe, and hit the bell icon for updates. Your feedback is appreciated. We hope to see you again.